In this video, we are going to talk about work, energy, and power. So let's start our discussion with work. So what is work? Work is defined as the product of force and displacement. So if you have got an object, let's say here is our object. So you are pushing this object with a certain force. Okay. Let's say you are using a force of 100 newtons. Now if this object is going to move from this point all the way to this point, okay, now let's say that the displacement is just basically d. Now let's call this one, let's say the displacement is 3 meters. Okay, so what is work? We are saying that work is the product of force times the displacement. Now let's shed more light. If we can see here, the force and the displacement, they are supposed to be going in the same direction. Now work is measured in joules, which we use the symbol J, capital J. So we do know that work is force times displacement, and we know that the force is in Newton. Okay, the force is in Newton, the displacement is in meters, meaning that 1 Newton meter is equal to 1 joules. As simple as that. Okay, now the displacement which we're talking about here and the force which we're talking about here, these two guys, they're supposed to be moving, or they're supposed to be in a straight line. Okay, so what we have to understand here is that when the force and the displacement, they are moving in the same direction, then work done is going to be positive. Okay, when the force and the displacement, they are moving in opposite direction, let's say the force is moving in this direction, the displacement is moving in this direction, the work done is going to be negative. Okay, what if the force and the displacement, they are perpendicular to each other? So if we have the force moving in this direction and the displacement moving in this direction, they are making 9. So if the force and the displacement, they are uh, making a 90 degrees, or we say perpendicular to each other, then the work done is 0. I'm going to explain why. The work done is going to be 0. So as long as you see that the force and the displacement, they are moving perpendicular to each other, then the work done is going to be 0. Okay, now let's shed more light. Why is the work done going to be 0 if the force and the displacement, they are moving in a perpendicular direction? Now let's see. We are saying that we have got an object here. This object, we are pushing it using the force of 100 newtons at a distance of what? At a distance of 3 meters. What is work? So work is force times the displacement. Okay, so work is going to be the force in this case is 100 times the displacement, which is going to be 3. So the work done is going to be a 300 joules. So the work done by the force is going to be 300 joules. Okay, now let's have a scenario where the force and the displacement, they are moving in an opposite direction. So this scenario is going to be a situation where an object is moving, but there is friction which is acting in this case. Okay, so let's say that this object is moving in this direction. Okay, or let's just do this. The applied force in this case, let's say the applied force is just basically 100 newtons. Then there is a force of friction which is opposing the motion. Let's say that the force of friction which is opposing the motion is 20 newtons. Okay, and this object has moved at a certain distance. Now let's say that the distance which this object has moved is let's say 50 centimeters. Okay, so what is the work done by the friction? Okay, and the work done by the applied force. So this is the applied force, this is the friction force. Okay, now we can see that the work done by the applied force, meaning that the displacement and the force, they are moving in the same direction, and we expect our work done to be positive. So work done by the applied force is going to be the force times the displacement. Work done by the applied force is going to be, we have the force which is 100, the displacement is a 500 centimeters. We have to convert these 500 centimeters into meters. So we're going to say is 50 divided by 100, which is going to be 0 0.5. So our work done by the force is going to be 0 0.5 times 100 is 50 joules. Okay, so 50 joules in this case is going to be the work done by the applied force. Now, what is the work done by the friction force? The displacement is moving in this direction and the friction force is moving in that other direction. Therefore, we expect our work done to be negative. Okay, so as long as the displacement and the force, they're moving in opposite direction, the work done is negative. Okay, so in this case we're going to say the work done by the friction force is going to be the friction force itself times the displacement. So work done by the friction force is going to be, the friction force is going to be 20. Now this 20 is going to be negative, so we're going to say negative 20 because it is opposing the motion, times 0 0.5, and we expect our work done by the friction force to be negative 10 joules. Okay, now another question here they can ask you is, what is the work net? Okay, so the work net, to find the work net, it is just the addition of the work done by the force, the applied force, and the work done by the friction force. In general, we subtract the work done by the applied force and the work done by the friction force. But since the work done by the friction force will always be negative, we add. Now adding it is the same as just subtracting it. So we're going to say the work done, the work net is going to be the work done by the applied force plus the work done by the friction force. Now what is the work done? So the work net in this case is going to be, the work done by the applied force is 50 joules plus the work done by the friction is negative 10 joules. Now from here we can see that our work net is going to be 40 joules. So this is our work net. Okay, now we have talked about the work done by the applied force, the work done by the friction force, and the work net. Now what if the force is applied at an angle? How do we find the work? Okay, so let's shed more light. Now let's assume to say you have an object. Okay, here is our object. This object, we are applying, let's assume to say the force which we are using, we're going to use a force at an angle, and let's call this one as theta. This is going to be our force. Remember we said the work done is equal to the force times distance, and we said these two guys are supposed to be in the same line, meaning that if we are going to have, if this object has been pushed all the way up to this distance here, meaning that the distance here is what we are going to call the d. Okay, we want to get the component of that force which is in the same line as the displacement or the distance. And which component is that? It's going to be the x component. So this force is going to have the fx and the fy, but we are trying to get the component which is in the same line with what? The displacement. Therefore we're going to get the fx. So if the force is applied at an angle, the work done is a force is going to be fx times the distance. But we know that in this case we have this. Here is our theta, here is our force, here is our fx, and here is our fy. To find fx using SOHCAHTOA, we can see that we are going to see that if we use sine, it's going to be sine theta. It's going to be the opposite divided by the hypotenuse. To find Fy is going to be the force sine theta. Meaning, if I want to come up with Fx, it's going to be cos theta is going to be the adjacent, which is Fx, divided by what? The hypotenuse, which is F. So my Fx is going to be F cos theta. Meaning that where there is Fx, I'm going to replace it with what? F cos theta. So there we go. Meaning that we're going to have the work is going to be equal to F cos theta times D. So this is the formula which we're going to be using when finding the work in all the cases. Now, in a case where the object is moving in a straight line, you are even applying the force, meaning the angle there is 0. If the angle is 0, or let me do this, we are saying that the general formula for work is equal to F cos theta times D. Remember I said when the force and the distance they are moving in the same direction, the work done is positive. And when the force and the displacement they are moving in opposite direction, the work done is negative. That's what I said. If the force and the displacement they are moving perpendicular to each other, the work done is 0. Now, this comes from this formula. This is the general formula for work. Work is given by F cos theta times the displacement. Now, let's start with the one which, if they're moving in the same direction, why is the work done equal to positive? So, if we have got an object, okay, this is our object here, moving in this direction, okay, then the displacement there, we assume that the displacement is there, meaning that this force is applied at an angle, but the angle, since it is moving toward east, the angle is 0. Okay, so you can have anything. If you do cos 0, cos 0 is 1, so therefore the answer is going to be positive. That's why we are going to see that this formula is just force times distance, because we know that even if we put cos 0, cos 0 is 1, so that is not going to affect anything. Okay, what if these two guys are moving in opposite direction? Let's assume to say we have friction. Friction is opposing motion, is moving in this direction in this case. Okay, why is the work done negative? If an object is moving, we know that force is a vector. If the force is moving in a opposite direction, or let's say it's moving toward west, the angle is 180. So what is cos 180? So we have the formula work to be equal to F cos theta times distance. So the theta here, since it is moving toward east, the theta is going to be 180 degrees. So if the theta is 180 degrees, we can say that what is cos 180? Okay, cos 180, we are going to see that is negative 1. So that negative 1, that's why we are going to see that if the force and the displacement they are moving in opposite direction, the work done is negative. Okay, now what if the force and the displacement they are moving perpendicular? Then perpendicular, the work done is 0. Why? Let's see. Here is our object. Let's say that um, you are lifting this, the force there is going up, then the object, you are moving in this direction, but you are lifting it up. So let's say that the distance is moving in this direction. Okay, we can see that the force here from this point all the way up to where the force is perpendicular, so it's making 90. So once you do work is equal to force cos theta. In this case, theta, if it is making 90 degrees, this theta is going to be 90 degrees times distance. What is cos 90? Cos 90 is 0, meaning that whatever you are going to have here is going to give us 0. So that's the reason why when the force and the displacement they are perpendicular to each other, the work done is 0. As simple as that. So this is what we need to understand under work. When they are moving in the same direction, the force and the displacement they are moving in the same direction. When they are moving in opposite direction, and when the force and the displacement they are in perpendicular. Okay, now let's solve some questions under the same topic. So let's assume to say we have the diagram here as we can see. Now let's assume to say the force there is 100 newtons. Then the displacement is moving in this direction as we can see. So the change in x, in this case, let's assume to say it is 200 centimeters. What is the work done? Remember, when the force and the displacement they're moving in perpendicular, or they're making 90 degrees, the work done is zero. So in this case, the work done is going to be zero joules. If you want, you can show it. You say the work is going to be the force F cos theta times the displacement, which is the change in x in this case. So the work is going to be, the force in this case is 100, because the angle is 90 degrees, then the distance is going to be 2. So you are going to see that the work done by the force is going to be 0 joules. So in this case, the work done is going to be 0. Okay, let's have the next question. So the next question is saying, how many joules of work are done by a bricklayer who lift a 1.5 kg cement block through 3 meters at a construction site? Okay, so let's come up with a free body diagram. So let's say here is the bag of cement, okay, and someone is trying to lift this bag of cement, which is 1.5 kgs. Remember, lifting meaning it will go in this direction. Okay, so that is the force they're talking about. Now the force of this block is going to be the weight of this block, mg. Now the distance, they're saying that through a distance of, they're not saying that they're perpendicular, no, but the distance is also in the same direction. So this 3.0 meters is also in the same direction. So since these guys are moving in the same direction, we expect our work to be positive. So work is going to be the force times the distance. You can even say F cos theta, because you know that in this case they are moving in the same direction. We expect to have our force to be it's going to be 1 actually. Okay, so in this case we're going to say the work is going to be the force which you have now. The force, since you are lifting, meaning that it's going to be the weight of this block, so it's going to be mg, okay, times the distance. So the work done by the force is going to be the mass, 1.5 times 9.8 times 3. So the work done in this case is going to be 1.5 times 9.8 times 3. So we expect our work done by the force to be 44.1 joules. As simple as that. Okay, so that is it for this question. Let's have the next question. So the next question is saying, an Eskimo returning from successive fishing trip pulls a lead loaded with salmon. The total mass of the lead and the salmon is 50 kgs, and the Eskimo exert a force of magnitude 1.2. 1.2. This is supposed to be 1.2 times and not 3. This 3 is not, it's not supposed to be here. So it's times 10 raised to the power 2 newtons on the lead by pulling on the rope. But how much work does he do on the sled if the rope is horizontal to the ground? Okay, and he pulls the lead at a distance of 5 meters. Okay, so we can even solve from here. They're saying that if the force is horizontal, it is not applied at an angle. Okay, so if it is horizontal, then they want us to find the work done. So if it is horizontal, it's not applied at an angle, the work done is going to be the force times the distance. So the force, we have been told that is 1.2 times 10 raised to the power 2 times the distance, we have been told that is 5, meaning that the work done in this case is going to be 1.2 exponent 2 times 5. So we expect our work to be 600 joules if it was moving horizontal, if the force which was applied, it was just horizontally. Okay, now let's go to part. So the work done when it was horizontally by the force is 600 joules. Now let's get rid of this. But B is saying how much work does he push or does he do on the slit if you use the angle 30 degrees. If the theta is 30 degrees, this one's supposed to be the theta. Okay, this one's supposed to be the theta, and he pulls the thread at the same distance, so the same distance, then at an angle of 30 degrees. Now as long as you have been given an angle, the work is going to be F cos theta times D. They're saying that the same force, the same distance, but the force has been applied at an angle. So the work done by the force is going to be 1.2 times 10 raised to the power 2 cos 30 times 5. So the work done is going to be 1.2 cos, we have exponent 2 cos 30, then times 5. So I'm getting my answer to be 519.62 joules. So that is going to be the work done by the force if the force was applied at an angle of 30 degrees. Okay, so this is part A, this is part B. So part B, the work done by the force when it was applied at an angle is 519.62 joules. Let's go to part C. Part C is saying at a coordinates position of 12.4 meters, the Eskimo leads up on the applied force, a friction force of 45 newton between the ice and the sled, bring the sled to rest at a coordinate position of 15.2 meters. So in short, they are saying that it started from 12.4, then it went all the way to 18 point. So we need just to say 18.2 meters minus 12.4 for us to find the distance. Now they want us to find the work done by the friction force. So the work done by the friction force is going to be the friction force times the displacement. But now in this case, the displacement, we have to say 18.4, 18.2 minus 18.2 minus 12.4. So we expect to have our displacement of 18.2 minus 12.4. We expect to have our displacement of 5.8. So 5.8 is going to be our displacement in this case. Now remember we said that since the displacement is moving in this direction, the friction force is moving in the opposite direction. Therefore we expect our answer to be negative. Now we do know that friction always opposes motion, so it's going to be negative. Okay, so the work done by the friction force is going to be, that friction force is going to be negative now, negative 45 times the displacement 5.8. So the work done by the friction force we expect to have I'm getting 261. So negative 261 joules is my work done by the friction force. So let me put it here. But see, the work done by the friction force is negative 261 joules. Now part C, we even talked about this when I was explaining about work net. So the question is saying, what is the work net? So the work net is the addition of the work done by the force plus the work done by the friction force. Now the force which we're talking about here, we're going to consider the force when it was horizontally. Okay, so that is the one which we're going to consider in this case, although the question is not specified to say we need to use the first one or the second one. But in this case we are going to assume to say Since the friction force was moving in this direction, we're going to assume that the force was but when they ask you this question, they are going to specify to say use the force use the force when it was applied at an angle, or you use the one which was horizontally. So in this case, let's just get to say it was horizontally. Okay, so I'm going to use 600. So I'm going to say that the work net is going to be, what is the work done by the force when it was uh, horizontally? So it is 600 plus the work done by the friction force, we know that is always negative, so it's 261. So we're going to have the work net to be equal to 600 minus 261. So I'm getting my work net to be 339 joules. So this is the work net. So this is what we need to know under work.